All right, so last time we were talking about if we had f of x equals x squared, so we kind of draw it off to the side, and we were going on the interval 0 to 2. Okay, and we were talking about finding the area under the curve from 0 to 2. And we were talking about an infinite number of rectangles. Okay, and we mentioned right-hand endpoints, and I told you that that was going to be the easier one. I'm going to show you now why right-hand endpoints are easier. Okay, so if I have 0 to 2, and I decide to use left-hand endpoints. Okay, I'm going to have these little rectangles, right? I'm going to have my ith rectangle, and so on. Okay, 0 to 2 means that every single width, which we call delta x, is going to be b minus a over n, which was 2 minus 0 over n, so it's going to be 2 over n. Okay, so the first rectangle, right, this is rectangle number 1, this is rectangle number 2, this is rectangle number 3. The first rectangle, if I use its left-hand endpoint, it's just 0. The second rectangle, if I use its left-hand endpoint, what is it going to be? 2 over n. The third rectangle, if I use its left-hand endpoint, it's going to be 2 over n times 2. The ith rectangle, if I use its left-hand endpoint, that point right there, what is the x value going to be? 2 over n times I minus 1, right? And we talked a little bit about that yesterday. Do you guys remember that? Vaguely. All right, so now there's this crazy notation, and all it means is that you're adding up the infinite number of rectangles. You're taking the height of each rectangle, and you're multiplying by the width of each rectangle. Okay, that's what that notation means. F just means whatever function you're talking about. In our case, it's x squared. So if I talk about f of whatever my x value is, and I'm using left-hand endpoints, on that ith rectangle, it's going to be 2 over n times I minus 1 squared. We're plugging it into the function f squared. All right, and then what's my delta x? What's the width of each rectangle? The 2 over n, not 2i over n. A lot of people put I. Okay, and I'm taking the summation of these, whoops, I forgot my summation, from I equals 1 to n. Okay, so we have to do some manipulating. We have to move it around, we have to simplify, and so on. I'm going to give myself more room here. Okay, so as I'm simplifying, I'm going to have I equals 1 to n. I'm going to have 4 over n squared, because I'm going to square the 2 over n. And then I'm going to square the I minus 1 squared. It's an I. And then I'm going to have times 2 over n. So what all can I pull out? Do you guys remember? I can pull out the 2 over n. I can also pull out the 4, nothing with I, the 4 over n squared. So I'm going to have the summation, and I'm going to have 8 over n cubed, and then the summation of I equals 1 to n, and I have my I minus 1 squared. So I'm going to FOIL it out. So I'm going to have my 8 over n cubed, and I'm going to have I squared minus 2i minus, or plus 1, from I equals 1 to n. Okay, and remember we talked about bringing a summation into a sum. Because what's really happening is if I start with 1, I'm going to have 1 squared minus 2 times 1 plus 1. I'm going to have that. And then I'm going to have 2 squared plus 2 times, or minus 2 times 2 plus 1. And then I'm going to have plus, remember that? So I can move everything around. So what I'm going to do is I'm going to have 8 over n cubed. I'm going to do a big bracket. I'm going to have a summation of I equals 1 to n, and I'm going to have I squared. Then I'm going to have minus 2 bracket, or not brackets, sigma, I equals 1 to n of I, plus sigma 1, I equals 1 to n. You see what I did? I just brought the summation of each piece. It's like I'm rearranging, and I'm taking all of these I squared, or all of the 1 squared, 2 squared, 3 squareds, all of those, I'm moving them together. And then I'm moving all the 2 times 1s, 2 times 2s, 2 times 3s. I'm moving those together and factoring out their common factor. And then I'm moving the 1, 1, 1, 1, 1, 1, 1. I'm moving them together. You guys see what I'm doing? I'm separating. Okay, and then you have those formulas. Running out of room. I'll go down here. So I have 8 over n cubed. And then I have my bracket. What about the I squared? Do you guys know what that is now? Anybody know?
n plus 1 plus 1 plus 1.
Yep. Good. See, I told you it'd take you like one homework assignment to know it. But I always give it to you guys anyway. Okay, and the next one, so I, that's the Gauss one. It's saying take your number of pairs, divide it, or the number of numbers, divide by 2, so it's the number of pairs, times the first number plus the last number. Okay, so we're going to have 1 plus n. So it looks like this in the formula. N times n plus 1 over 2. And then the last one, if I add up 1 n times, I get n. You with me? I'm going to go ahead and distribute my 8 over n cubed to each one. Okay, so I'm going to have 8 n. I'm going to go ahead and FOIL these two out. So I'm going to have 2n squared plus 3n plus 1 all over 6n cubed minus these twos will at least reduce out. So I'm going to have 8 times n plus 1 over 6. No, not 6, over n cubed. Almost got a bonus point. Were you on it? All right, and then plus 8n over n cubed. Okay, so we're just distributing the 8 over n cubed n. And then I can reduce out. So like an n cubed will now become n squared. The 8 and the 6 make 3 on the bottom and 4 on top. So I get 8n squared plus 12n plus 4 all over 3n squared minus, and the n cubed make n squared. So 8n, I don't know if I want to distribute my negative or not. I'll leave it in parentheses. Plus 8 all over n squared plus 8 over n squared, because the n and the n cubed. Still with me? All right, so I have 8. I'm going to bring this 3n squared into each piece. So I'm going to have 8 over 3 plus 12 over 3n plus 4 over 3n squared. I guess that could be 4 over n right there, right? Instead of 12 over 3. That's fine. All right, minus 8 over n minus 8 over n squared plus 8 over n squared. And things will reduce out. Like I said, you can get a 4 here and a 1. But what we're really worried about is at the very end, what do? We want, as we have an infinite number of rectangles, so we do a limit. So we do the limit as n goes to infinity, and what do we get? Yeah, because all of this goes away. It's all over n, over n, over n, over n, over n. Right, all of it goes away except for that very first thing, which is 8/3. Okay, so annoying. It's harder when you have the I minus 1, because right here you have to FOIL it out, right? And then it gets complicated. It's a harder summation. So you should always use your right-hand endpoints if possible. Left hand is always harder, okay? All right, so let's try some more. So it says find a formula for the sum of n terms for the function f of x equals 2x minus x squared on the interval 0 to 1. Find the limit as n goes to infinity. I think this might be one that I gave you on your homework too. It's not good. Okay, so anyway. So we're going to have 2x plus x squared on the interval 0 to 1. So let's first think about what the graph looks like. Do you guys know what the graph looks like? If I set it equal to 0 to find where it's crossing the x-axis, it's crossing at 0 and at 2, and it's a downwards parabola. So it's looking something like this. And we're only going on the interval 0 to 1. So right here. Okay, so I just told you the easiest thing to use are right-hand endpoints. So that's where I usually kind of draw a little number line to help me. So 0 to 1. That's nice because now when I talk about my delta x is 1 minus 0 over n. It's just 1 over n. So if I'm talking about my ith rectangle, and I want my right-hand endpoint, think about it. The first rectangle would be at x equals 1 over n. The second rectangle would be at x equals 2 over n, right? 1 over n times 2. Do you guys see it? So the ith rectangle is at what?
What's the delta x again? There's only 1 minus 0. Is it the x minus the y or what?
It's delta x is always b minus a over n. It's the width of the rectangle. Okay, so the ith rectangle has x equals I over n. That's right. So what we're going to do is we're going to replace our x values with I over n. So in my summation formula, it's always your function evaluated at the ith rectangle using whatever endpoint you want. So in this case, we want right endpoints. So my function is 2x, so 2 times I over n, minus I over n squared, right, x squared. That's my function. You nervous? And then times the width. The width is 1 over n. Height times width. So I'm going to have I equals 1 to n, and I'm going to simplify it out. Okay, so this is what I'm asking on the second homework assignment I gave you. Okay, I'm asking you to do things like this. This is algebra. It doesn't look like algebra, but it is algebra. You can do this, I promise. Okay, so we're going to have I equals 1 to n. I'm going to have 2i over n minus I squared over n squared. But then I still have multiplied, like all of that's in parentheses, multiplied by n, or 1 over n. So I'm just going to gain an n on the bottom. So I'm really going to have 2i over n squared minus I squared over n cubed. And are you seeing you can pull the summation in? Okay, so I'm really thinking of it as this. I equals 1 to n of 2i over n squared minus I squared over n cubed, like that. What can I pull out? Anything that has that n, right? Like the 2 over n squared, I can pull that out of the first one. So I'm going to have 2 over n squared, summation I equals 1 to n of I. Well, we know how to do that. That's the Gauss thing. Right? Minus 1 over n cubed of the summation of I equals 1 to n of I squared. And we know how to do that because Jess just told us she memorized it. So we're good. We got it. Okay, so I have 2 over n squared times n plus 1 over 2. That's the Gauss one. You have known that since Algebra 2. We did it in Chapter 11 in Algebra 2. All right, minus 1 over n cubed times n plus 1 times 2n plus 1 over 6. And we simplified. Do you guys want to try to simplify it and take the limit as n goes to infinity? See if you can get it? Okay, I'll give you a second to try it. Anybody have any guesses? Did you get there yet? I hear mumble, mumble, mumble.
Okay. So, I don't know if you said, but is it like 2 plus 1 over 2?
I don't know. Did you take the limit? You need to take the limit.
Oh, yeah, that's right.
All right, so let's cancel some different things. So like the 2 and the 2 reduce out. The n and the n squared reduce out to n. So you have n plus 1 over n minus the n cubed and the n reduce out. So you have 2n squared plus 3n plus 1 over 6. So bring the n into everything. Ah, 6n squared, darn. Abby got me. Was it Abby? Is that your second bonus point of the semester already? Jeez. Mm-hmm.
Since you now have like 1 time n plus 1 over 2n plus 1, can you like cancel out n plus 1 like minus the n plus 1 over there?
No.
2n plus
Like this n plus 1 here?
Yeah.
No, because it's being subtracted. It's not like it's not being divided or anything like that. Like you can't cancel them.
I mean, like not cancel, but like they equal 0.
We don't think so.
Okay.
Okay, so the next one. So I have n plus 1 on top over n minus, I have my 2n squared plus 3n plus 1 over 6n squared. Okay, so I'm going to bring the n into both pieces. So I'm going to have 1, right, n over n, plus 1 over n, minus, and then I'm going to bring the 6n squared into each piece. So that's when I would have realized my error if Abby hadn't corrected me, because I realized I have n on top and not on bottom. It would go to infinity. These won't go to infinity. It is a finite area that's trapped. Okay, so I have 2n squared over 6n squared, which reduces out to 1/3, plus 3n, actually a minus 3n over 6n squared because I'm distributing the negative, and then a minus 1 over 6n squared. So I'm going to have 1 plus 1 over n minus 1/3 minus 1 over 2n minus 1 over 6n squared. Did you guys get anything like that? Okay, close. Now take the limit as n goes to infinity. This goes away, and this goes away. They all go to 0. So I get 1 minus 1/3, so I get 2/3. So your answer should be 2/3. Yes? Uh-huh. Because I took the n plus 1 and I divided by n, which means I had n over n plus 1 over n. So it became 1 plus 1 over n. I brought the n into both pieces. All right, you getting it? Kind of? Okay, let's try another one. Okay, so we sometimes call this Riemann approximations. Riemann is the guy who came up with the rectangular method. So when you hear Riemann, think rectangles. So my teacher never even used his name. I was like, who's Riemann? And it was on my AP test. I remember that. It was like, use a Riemann approximation too. And I was like, I don't know what this is, right? So it's a rectangle approximation. So you're going to use some kind of rectangle. All right, so very German. You can say it very throaty German if you want to. No. George Friedrich Bernhard Riemann. I will not do the throaty. You can if you want. Okay, so he studied under, remember that annoying 10-year-old that added up 1 through 100? Yeah, he became famous in the math world. Carl Friedrich Gauss. So he studied under him, and he came up with the rectangular method of area approximation. So we've talked about right-hand sums and left-hand sums, and you guys had that on your day 1 homework, right? We will also learn something called the midpoint rule. So the midpoint is when you take a rectangle and you go straight across wherever its midpoint matches up with the curve. So let's say I'm talking about here, then that rectangle would be like here. Does that make sense? So like the height of the rectangle is where the midpoint of the interval is. Okay, so we could also use those approximations. Okay, so it says consider the region bounded by the graph of f of x equals the square root of x in the x-axis on the interval 0 to 1. Okay, we're going to evaluate the limit, this Riemann sum, where ci is the right endpoint of the partition that is given randomly by this. Okay, this means that they are not all the same width. This is a really, really strange one. You don't have to have them all the same delta x. They could be like, some could be skinny, some could be big, some could be skinny. It doesn't matter. If you take an infinite number of rectangles, they'll all end up being very tiny. It doesn't matter. So we're doing this random partition that is actually going to be quite useful to us because we have the square root of x. Okay. So let me kind of show you what we're talking about. Okay, so as we're going on the interval 0 to 1. Okay, and it says c sub I is equal to I squared over n squared. So if I want the first subinterval, C1, it's going to be 1 squared over n squared. So I'm going to get 1 over n squared. So this distance is 1 over n squared. And then if I'm just plugging in the I squared over n squared. That's the first interval. That's the first right-hand endpoint. If I want the second endpoint, it's going to be at 2 squared over n squared. So it's going to be at 4 over n squared. Okay, that's going to be 4 over n squared, right? That's going to be where the x value is, 4 over n squared. So this first one had a distance of 1 over n squared, whatever n squared is. And the second one, so this was delta x equals 1 over n squared. What's the second delta x? 3 over n squared. It's telling you the difference between them. Do you guys kind of understand what I'm saying? So they're all going to be different. So the next partition, if I want to talk about the third rectangle, it's going to be at 9 over n squared. So that one's going to be 5 over n squared is the distance. What are you stuck on, Hannah? Yeah, I'm just subtracting. 9 minus 4. It's 5. What would the next one be? 16 over n squared. So what's the difference there? 7 over n squared, right? Okay. So the reason we do this is, I mean, it's nice for us because we're taking the square root of x. And so we want our x values to be something where we can easily take the square root of it. Okay, so if I set up my limit, or set up my sigma, I guess, I'm going to have the height of the rectangle. So if I talk about this first rectangle, it has a height of 1 over n squared. Or it has not a height, it has the x value of 1 over n squared. The second rectangle has an x value of 4 over n squared. The third rectangle has an x value of 9 over n squared. Do you guys see how it's working? So the ith rectangle, so if I talk about the ith one, what is its right-hand endpoint? I squared over n squared, which was given to us. It was this. Okay, so I'm going to have the square root of, because that's my function, I squared over n squared. Do you see why we randomly chose this interval, or this partition? All right, times delta x. Delta x in this case is not b minus a over n. They're not equal widths. So how do I get it? It's I squared over n squared minus what? You're really close. I squared over n squared minus the one before, right? Minus I minus 1 squared over n squared. That's what it is. That's the width. Yeah, that's like when I was writing the 1 over n squared, 3 over n squared, 5 over n squared. That's the width. Do you guys understand what I'm saying? So when I come up with these, so when I simplify it, I have I squared over n squared minus I squared minus 2I plus 1 over n squared. And if I have common denominators, so I'm going to combine. I have my I squared minus I squared, it goes away. So I get 2I plus 1 over n squared. That is the width for every single one. So for instance, when I talked about that third rectangle, it had a width of 5 over n squared. If I plug in 3 for my I, wait, let me think. 1, 2, I made a mistake, didn't I? It should be minus. Good thing I checked that. 2I minus 1. Could have gotten a bonus point. Man, just so speedy. Okay, so if I, for the third rectangle, if I plug in 3, do you guys see I get 2 times 3 is 6, minus 1 gives me the 5 over n squared. For the fourth rectangle, you could plug in 4. So that's what it's going to be. So I'm going to have 2I minus 1 over n squared. And I'm going to go from n equals, or I equals 1 to n. Do you guys want to try to simplify again? No, you just want me to do all the work. You're going to have to do this on your homework. Do you realize this? Are you going to be okay on your homework? Yes.
I have a question. So sometimes when like we have I squared a while back, it would be equal to -1. Is that the same thing?
No, I, J, and K are typical subscripts for sigma notation. Okay, I, J, and K. I does not mean the square root of -1. Okay? All right. Let me insert a new page. Okay, so what did we have? Let me go back to the last one. So the square root of I squared over n squared times 2I minus 1 over n squared. Okay, so we have this. I equals 1 to n. Have an open mind. Most of this is algebra. You guys have been begging me to go back to algebra 2. This is algebra. This is reducing, multiplying out, foiling. That's algebra. That's what you guys have been begging to do. All right, so what is this?
The height?
No, what is it? If you take the square root. It is the height, but it's I over n times 2I minus 1 over n squared. Okay, so on the bottom, I definitely have n cubed. On the top, if I take my I times 2I minus 1, what do I get? 2I squared minus I.
Oh, never mind.
It is foiled. Or not foiled, I distributed. Okay. I'm going to break it apart. So I'm going to write it as 2i squared over n cubed minus I over n cubed. So I'm just breaking it apart with common denominators. Okay, so then I'm going to break apart my sigmas. Remember, I can distribute a sigma n, basically. So I have 2i squared over n cubed minus sigma I over n cubed. All this is just rearranging terms. It's putting all of the first terms with all of the first terms, all the second terms with all the second terms. What are you allowed to pull out?
N.
N's. Can I pull out the number? Yeah. So I'm going to have 2 over n cubed. And I have the summation of I squared, which by now you should all know, minus 1 over n cubed, and I have the summation of I. So don't just copy what I'm writing, think about what I'm writing. Think as you are writing. So I get 2n cubed times n times n plus 1,
So 2 over n.
2 over n cubed, yeah. You don't get bonus points for what I say. I say the wrong thing too much. I'm writing and talking. You know how hard it is to write and talk? It's very difficult. Yes?
Is the I squared minus, is that I over n cubed? Or is that 1 over n cubed?
I over n cubed.
Pull up the 2 over n cubed, and then it goes,
This one is 1 over n cubed.
uh,
This one is I over n cubed. Because the I is still on the inside. Yes?
So when we're finding the second one, like just the I by itself,
When you're finding the second one,
like,
this one,
yeah. So you plug in 1 for I, and then, but how do you know what it goes to?
I don't know what you're saying. Like, what this literally means right here is 1 plus 2 plus 3 plus, is that what you're saying? It goes to whatever n is. N is infinity. It's going to go to infinity.
So like, if we were like on our homework, if it was, if like that I equals 1 to the I, there was like a number 20 on the top.
Then you would stop at 20.
Okay.
All right, so the next one. So if I have the summation of 1 plus 2 plus 3 plus 4 all the way to n, remember this is what Gauss did when he added up the numbers 1 through 100. Okay, so we're taking n over 2, right, the number of pairs, times the first term 1 plus the last term n. So it ends up being n times n plus 1 over 2. Okay, now we simplify. Is this the part that you guys like? You like it when it gets here? Can you do this part? So we'll pause. I'll let you guys try it. Then take the limit as n goes to infinity. All right, so the 2 and the 6 reduce out. The n and the n squared make, or n and n cubed make n squared. You FOIL, so you get 2n squared plus 3n plus 1. I always wonder why they just don't give you that, you know, because you're going to FOIL it out every time anyway. Minus n and n squared is, or n and n cubed make n squared. So I have n plus 1 over 2n squared. Okay. And I'm going to bring the 3n squared into each piece in the first one. So I'm going to have 2 over 3 plus 1 over n plus 1 over 3n squared minus, now I bring the 2n squared into each piece, so I have 1 over 2n minus 1 over 2n squared. Did you guys get that? Okay. Now I take the limit as n goes to infinity. Gone, 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 gone. I get 2/3. Did you guys get 2/3? Okay. So you still have to do the i's part. You got to know how to pull all those things out. You got to know how to change the sigma around. But then once you get there, it seems like you're pretty good. Nia, do you have a question?
how should you go 1 over 2 then?
I distributed the negative, and then I brought the 2n squared into both pieces. So I have negative n over 2n squared minus 1 over 2n squared, and this reduces out. So negative 1 over 2n. Lots of algebra. Okay, so what is this? So this whole process, like I said, remember, just like definition of derivatives, we have to learn all the hard stuff first. We have to learn how they came up with these things because this is how it's done for a long time. They did rectangles. You guys are very lucky. We don't do this anymore. We learn shortcuts. It's very nice. It's the same thing in your chemistry class. You guys remember you always had to learn like what they learn in order. Same thing. You have to know the basics before you like learn all the shortcuts. So what this is this formula, right? Finding the sum of all those rectangles with their heights and their widths. It ends up being something related to our antiderivative. Okay, so this little sign is called an integral sign. Integral sign. So it's the integral from a to b of your function f of x dx. Okay, so what that represents is as long as f of x is positive, as long as we have some kind of function above the curve, what it means is that it's the area from a to b on a certain interval. It's basically adding up that infinite number of rectangles. It gives you that positive area. It's the area that's trapped in there. Okay, so there's going to be weird things as it dips below the curve and so on. We'll talk about that. Okay, so let's talk about this one. So it says for f of x equals sine of x on 0 to 2 pi, hopefully you remember how to draw your sine function. You start at 0, 0. You go up to a height of 1. At pi, you go through the axis again. You go down, and then at 2 pi, you cross. So it says give an area interpretation of this. So it's saying multiply all your heights by all your widths. What do you think you'll get if I do the area from 0 to 2 pi of sine of x? We always put a dx too. Dx just tells us what variable we're using. Okay. Well, what's the height here? 1. What's the height here? -1. Do you think the height times the width cancels each other out with those two things? They do. They cancel each other out. So I have my height, and then I have a negative height. I have a height, and then I have the negative height. They're always going to cancel each other out. So what do you think the interval is going to be? 0. Okay. So sometimes we're going to have positive integrals. Sometimes we're going to have negative integrals. It depends on if you're above the axis or if you're below the axis. In this case, it was a positive number and a negative number, and they add up to be 0. They're exactly the same value. They're just add up to be 0. All right, I want to show you the setup for the next one because you have it on your homework. If you're doing a midpoint rule, notice how it's saying from 1 to 2. So we're going from 1 to 2. And n equals 5. What does that mean? 5 what? 5 rectangles. Okay? If I divide that length of 1 into 5 pieces, I'm going to have every 1/5. So this is going to be 1.2, 1.4, 1.6, 1.8. Right, 0.2. Do you guys see how it makes 5 rectangles? Now, if I want to use a midpoint, what I'm doing is I'm not using 1.2, I'm using 1.1 to get the midpoint. I'm going to use 1.3, 1.5, 1.7, 1.9. And all you're doing is you're finding the heights at those different points. Do you guys understand what I'm saying?
Why are we doing it?
Because we're using the midpoint of the interval. So if I divide it into widths of 0.2, what I'm going to do is I'm going to use the one in between it. So if I have from 0 to 1 or 1 to 1.2, I want to use the midpoint to get the height. So we're not using right endpoints, we're not using left ones, we're using the one in the middle. We're using 1.1. So you have one like that on your homework where you're going to use the numbers in the middle to plug them into the function. But it's very easy. It's not an infinite number of rectangles. It's just like 4 rectangles. So you guys can definitely do that. All right. Okay, so